Hello everyone, this is Lesi. I'm sad that I cannot attend the COLT conference in person due to the research issue, so I have to present our paper online. This video contains the presentation of our COLT 2024 paper entitled On Finding Small Hypergradients in Bilevel Optimization, Hardness Results and Improved Analysis, joint work with Jing and my PhD advisor, Zhang. In this paper, we consider the following bilevel optimization problem, where we have two objectives, f and g, and two variables, x and y. Our goal is to minimize f with respect to x, subject to g is minimized with respect to y. This formulation covers many applications, including hyperparameter tuning, meta learning, and neural architecture search. Take the hyperparameter tuning as an example. In this problem, x represents the hyperparameter and y represents the other parameters. For this problem, a well-studied setup is when the lower-level function is strongly convex. Then this problem is equivalent to minimize phi x, which is fx y star x. Now y star x is a singleton due to the lower-level strong convexity assumption. And the implicit function theorem implies the differentiability of phi x. And we can use the explicit form of phi's gradients as described in equation 3 to perform gradient descent on phi x, which will converge to its stationary points. However, in many applications, we do not have such a strong convexity assumption as assumed by all these previous works. Our work aims to study whether convexity as a relaxation of strong convexity suffices for finding small hypergradient efficiencies. Now, as we do not have the strong convexity, we have to minimize y twice. The first time is to minimize with over g, but now y star x is a set instead of a singleton, so we have to minimize the second time over f to make the hyperobjective well-defined. For this hyperobjective phi x, we ask that can we find its stationary points when the lower-level function is strictly convex or merely convex, but not strongly convex. The first challenge without lower-level strong convexity is that phi x can be discontinuous, as we show in this example. This example is also provided in our paper. You can see in this example that the lower-level function is a bilinear function and thus clearly convex in y, but not strongly convex. When in this example, when x is greater than 0, g is minimized when y is also 0. When x is less than 0, then g is minimized when y is 1. Therefore, phi x becomes discontinuous at the origin x is equivalent to 0. From the previous slide, we know that phi x may be discontinuous, and this discontinuity comes from the discontinuity of the solution set y star x. Formally, in our paper, we can prove the following results that under regular conditions, phi x is continuous if and only if y star x, the lower-level solution set, is also continuous. As it is set, we defined the continuity of this set according to Popov and Haushoff. Then we study a lighter, stronger condition. when the low-level function is strictly convex. Similar to the strongly convex case, we can use the implicit function to prove the differentiability of phi x. And we ask, can we find stationary points of phi now? But the answer is no, because it suffers from computational issues. And we prove the following theorem in our paper. You can check our paper for the formal claims. And we prove that there exists a bilevel optimization problems instance whose low-level function is strictly convex, and F3 satisfies some regular smoothness conditions, such that any zero respecting algorithm gets stuck at the origin, at the initialization, x0. And we want to remark that the definition of zero respecting algorithms includes most first-order algorithms for bilevel optimization problems. Formally, we define the zero respecting algorithms on this problem, which is a special case of the general bilevel problem, where G does not depend on X. For this problem, standard first-order algorithm consists of two loops, as we present in this slide. The inner loops perform k-steps gradient descent on Y using gradients of both F and G, and the outer loops use YK as a approximation of Y star, and then apply the gradient descent on F, X, YK. In our paper, we construct hard instances F and G such that any zero respecting algorithm would fail for this special bilevel problem. This shows that bilevel optimization is really hard without low-level strong convexity assumption, because even this special case is hard enough. And we remark that our construction is inspired by Nestrov's lower bound function for convex optimization. And we set to G to be a function that's similar to Nestrov's worst-case zero trend, such that any first-order algorithm would have a slow progress when optimizing G. And as it is a bilevel problem, when the optimization progress in G is slow, then this problem is very hard to solve. And this is the intuition in our construction. Given our negative results, we aim to study intermediate function classes that are not strongly convex but still be computationally trackable. In particular, we study the cases when the lower level function satisfies the polyarc Lesi condition, PL condition for short. And this is the definition of this PL conditions, which assume that the gradient of this function can dominate its suboptimality gap. This condition is considered by previous works such as quantized dot, shouted dot. However, merely PL condition on G does not suffice to guarantee the differentiability of the hyperajective phi x. And we also give an example in our paper. And following quantized dot, we further assume that the penalty function defined in this equation is also PL for small sigma. Under this additional assumption, quantized dot proved the differentiability of phi x. This is a good setup because phi is now differentiable as the strongly convex case. And we can define the task of finding its stationary points as its gradient exists. And we will consider this setup in our paper. For this non-convex PL setup introduced in the previous slides, we prove new upper complexity bounds. And we generalize the F² BA algorithm, namely fully first-order bilevel optimization, which is also proposed by our group in 2023. This algorithm is originally designed for strongly convex functions, and we generalize this algorithm to PL functions. In this way, we can achieve better complexity upper bounds for this non-convex PL setup. This algorithm simply applies gradient descent or GD to the penalty function as described by equation 6. This penalty approach penalizes the suboptimality gap of G to F, and this can be viewed as a soft constraints version of the original hyperobjective, which is defined by hard constraints that Y must be lie in the lower level solution set. But now we have the soft constraints. And in this paper, we show that it is possible to restrict the analysis of the original F-squared BA algorithm in a strongly convex subspace implied by the Bilevel conditions, so that most results of F-squared BA also holds for PL problems. In this way, we can achieve the best known complexity upper bounds for this setup. And we compared our results with previous works in this table. Compared to Schultz et al., which is published at Conference Neuros 2023, our method does not require second-order oracles, which is expensive in practice. And hence our method is more practical since it's fully first-order. Compared to COLT et al., our method has better complexity in terms of epsilon in both the deterministic and stochastic setting. By the way, the dependency on our condition number kappa is also the best compared to all these previous works. And in summary, our paper studies bilevel optimization problem without the typical lower-level strong convexity assumptions. And for the task of finding small hypergradients, we prove that non-convex convex bilevel problems are intractable if we do not have the lower-level strong convexity. And second, the non-convex PL bilevel problems are as easy as strongly convex case. Thanks for listening.